By the end of the presentation, you should be able to answer the following questions. How does temperature relate to pressure? How does pressure relate to volume? And what are the main points of the kinetic molecular theory? All right, these are conversions that y'all will need to know. The first four are all pressures, so atmosphere, millimeters of mercury, kilopascals, and torr, those all measure pressure. So those would be your units for pressure. K is Kelvin. This is actually degrees Celsius, plus 273. When you do gas laws, everything except for Boyle's law has to be in atmospheres and Kelvin. And if they're not, you need to convert. All right, Boyle's law. Boyle's law says that pressure and volume of a gas are inversely proportional when temperature is held constant. And here is the equation. So you can see, and this is kind of almost common sense, if you increase the pressure on something, you're going to decrease the volume. So when you graph it, and you will need to know how to graph these. When you increase volume, you decrease pressure. Or if you do it volume versus pressure, you decrease volume, you increase pressure. All right, the volume of the lungs is measured by the volume of air inhaled or exhaled. If the volume of the lungs is 2.4 liters during exhalation and the pressure is 101.7 kilopascals, and the pressure during inhalation is 101.01 kilopascals, what is the volume of the lungs during inhalation? Okay, so like I said, for Boyle's law, as long as your units are the same, kilopascals, that's fine. It doesn't have to be in atmospheres or liters. So our equation is P1 times V1 equals P2 times V2, or initial and final. So our initial pressure was 101.7 times our initial volume, which was 2.4, equals our final pressure times our final volume, which we don't know. I'll plug it into the calculator algebra, and you get 2.41 liters. If a piston compresses the air in a cylinder to half its original volume, which is 930 milliliters at STP, what is the pressure after the gas is compressed? Okay, STP is standard temperature and pressure. Standard temperature is 25 degrees Celsius, or nope, that's for thermodynamics. Don't listen to me. For gases, standard temperature is 273 Kelvin, and pressure is 1 atmosphere. Okay, we want to know what the pressure is after the gas is compressed. So our original pressure is at STP, so 1 atmosphere times, I'm going to convert it to liters because that's what I did when I worked these out. So 0.930 liters equals 0.465, because that's half, right? It says it's half the original volume times the second pressure. A little algebra, and we get 2 atmospheres is our second pressure. All right, Charles' law. Charles' law says the volume of a gas is directly proportional to the temperature. So if volume increases, temperature increases, or if temperature increases, volume increases. So your graph would look like this, okay? A sample of neon gas occupies a volume of 752 milliliters at 25 degrees Celsius. What volume of the gas occupy at STP if the pressure remains constant? So when it says something remains constant, that means you don't worry about it. So we're not going to worry about pressure. We do, however, have to worry about converting these. So we need to convert 752 milliliters to liters. So there's 1,000 milliliters in 1 liter. So 0.752. And then Celsius to Kelvin. All you have to do is add 273 equals, what did I get? 298 Kelvin liters. All right, then we're going to plug it into our equation. V1 over T1 equals V2 over T2. So our first volume was 752, well, 0.752 liters at 298. And then we don't know our second volume at standard temperature, which is 273. All right, a little bit of algebra, and we get 0.689 liters. A gas occupies 900 milliliters at a temperature of 27 degrees Celsius. What is the new volume if you increase the temperature to 56 degrees Celsius? So our conversions, this will convert to 0.9 liters. 27 plus 273 gives us 300 Kelvin. That's our first temperature, and then our second temperature is 329. Okay, so we're going to plug it into Charles' law. So our first volume was 0.9. First temperature was 300. We don't know our second volume, and then 329. All right, after a little bit of algebra, we get I can't tell if that's a 9. We're going to say that I wrote down a 1 and hope that I'm right. Liters. Okay. Whoops. All right, Gay-Lussac's law. The pressure of a gas is, again, directly proportional to the temperature. We don't really use his law much, other than that we use it in the combined gas law. So we're going to combine Boyle's law, Charles' law, and then Gay-Lussac's law, all in one. And so if you can't figure out which law to use, then use the combined gas law, plug your stuff in, and if it says one is held constant or it doesn't give it to you, then just ignore it. And you'll probably get the right answer, at least hopefully. Okie dokie. So 5.36 liters of nitrogen gas are at negative 25 degrees Celsius and 733 millimeters of mercury. What would be the volume at 128 Celsius and 1.5 atmospheres? Okay, so everything needs to be in liters, atmosphere, and Kelvin. So we got some converting to do. So let's do our millimeters of mercury real quick. So remember those conversions I gave you at the beginning of the slide? In 1 atmosphere, there's 760 millimeters of mercury, which those cancel out, and I got 0.96 atmospheres, and I'm running out of room. And then negative 25 plus 273 gives 248 for my first temperature, and then 128 plus 273, and I get 401 for my second temperature. Okay, now I can plug everything in to the combined gas law. So P1V1 over T1 equals P2V2 over T2. Okay, so what do we have? Our first pressure, 0.96 atmospheres times 5.36 liters over 248. 1.5 atmospheres times, we don't know, over 401. Okay, little algebra, and we get 5.55 liters. Okay, why don't y'all pause it and do this one on your own, and then check your answer. So I got 3 times 0.025 over 298. I hope you'll converted everything you needed to convert. Didn't know that. This is our volume. I just wrote it backwards. Okay, little algebra, and I hope you got 2.82 liters. Alright, Avogadro's law. So Avogadro's law says that volume is directly proportional to the amount of moles in a gas. So this is what your graph would look like. And basically, if we have the same volume of gas at STP now, so our pressure and our temperature are always 1 atmosphere, 273, it means that 1 mole of gas will always be this volume, 22.4 liters. And we're going to use that for stoichiometry. So how many grams of aluminum chloride must decompose in order to produce 3.10 3.10 liters of chlorine at STP? Okay, for you to use that conversion of 22.4 liters per mole, it always has to be at STP. If it's at something else, then you got to do other stuff that we're not going to do in this class. Okay, so make sure your equation's always balanced, and then start with what they gave you. 3.10 liters of chlorine gas. So I want to use my mole ratio to change substances, so I got to get this out of liters. So 1 mole of chlorine gas is going to be 22.4 liters at STP. And then now I'm going to do my mole ratio, 3 moles of chlorine gas to every 2 moles aluminum chloride. That cancels, my liters cancel. And then it wants grams, so I need to use molar mass. So 1 mole of aluminum chloride is 133.33 grams. Okay, so that cancels. All right, multiply across the top, divide by what's on the bottom, and I got 12.3 grams of aluminum chloride. Okay. Dalton's law. Basically, Dalton's law says the sum of the partial pressure of each gas will give you the total pressure. So like air is composed of all these different gases, and they all have different pressures. Well, you add them all up, and you'll get the total pressure. So this is pretty simple. So if the total pressure of a container is 3.6 atmospheres and contains 2.4 atmospheres of hydrogen and then some other gas, what is the partial pressure of the other gas? Well, we know that P total is equal to P1 plus P2. So we know our P total is 3.6 atmospheres. We know this hydrogen was 2.4 atmospheres plus X. We don't know. So just subtract and you get 1.2 atmospheres for that other gas. It's pretty simple. Alright, the ideal gas law. This is the last law. So P is obviously for pressure, V is for volume, T is for temperature. Now we've got a little n for the number of moles. And a big R is your gas constant. This is your gas constant down here. Okay, this is on your reference chart. And actually I use 0.0821 moles per Kelvin per atmosphere times liter. So how much pressure does 4 moles of nitrogen gas at 30 degrees Celsius exert on a container at 55 liters of gas? We still have to convert our temperature to Kelvin, so 30 plus 273 is 303, right? Yeah. Alright, I'm going to plug it into the ideal gas law. Pressure is, I don't know, times 55 liters equals 4 moles times my gas constant, which is 0.0821, times my temperature, 303, little algebra, and I get 1.81 atmospheres. How many grams of carbon dioxide do you have if the gas is exerting a pressure of 1.3 atmospheres, 28 degrees Celsius, in a container that holds 3 liters of gas? Alright, y'all pause it, check your answer. So I'm going to plug it into the ideal gas law. I don't know, oh no, I do know my pressure. It is 1.3. 3 liters. Oh, I don't know my moles. 0.0821. And my temperature is 301. Alright, algebra gives me 6.3, looks like a 7 moles of carbon dioxide. But they wanted grams. So, molar mass, 1 mole carbon dioxide, I used 40.01. I don't know if that's right. I can't remember. Oh no, 44. It's 44. Oh no, that didn't sound right. and so I get 0.14 grams of CO2. All right, kinetic molecular theory. Yes, write this all down because you'll have to know these. All right, so the postulates are gases consist of large numbers of molecules or atoms that are in continuous random motion, which is, a lot of this is just common sense, right? Gases are always moving fast. The volume of the actual molecule is negligible compared to the total volume in which the gas is contained. So basically that says if we have like a beaker of, say, a 1 liter beaker, and it's filled with gases, we're going to say the whole volume of the gas is 1 liter instead of trying to measure each one of these little tiny molecules. That's not going to tell us the volume. The volume of the gas is the total, okay? And attractive forces between gas molecules are negligible, right? That would make sense. If they were really attracted to each other, like a liquid or a solid, then it wouldn't be a gas. If they were really attracted to each other, then they'd be a solid. So what do these things tell us? Well, it tells us the average kinetic energy of the molecules do not change with time, okay? They can bounce around, but they don't really slow down as long as the temperature of the gas remains constant, okay? Now, if you increase the temperature, you're going to increase your average kinetic energy. Energy can be transferred between molecules, but it's not lost. They're called elastic collisions, okay? They're not sticky, basically. And kind of just said this, the average kinetic energy of the molecules is proportional to absolute temperature. At a given temperature, the molecules of all species of gas, no matter what size or shape, and I think this was one of those questions on the benchmark, number 1 actually, or yeah, I think so, have the same average kinetic energy. Alright, so if you can't answer the questions at the beginning of the slide, then please watch it again.